So welcome to the last lecture of this course. And so yesterday we discussed the relativistic form of the Maxwell's equations. And so we discovered that we can introduce a tensor f mu nu with two indices, which is antisymmetric. So the people typically to distinguish to explicitly state the symmetries, so they would put like this skew thing on the indices mu and nu, indicating that actually the indices are antisymmetric sometimes. If they were symmetric, I would put this thing here. But let's not write it here. So it's antisymmetric tensor, and because it's antisymmetric, it has 6 independent components, and these are precisely given bioelectric and magnetic fields. And you can also write it in this nice form. So by the way, this is really tied to our inertial coordinates, which are basically Cartesian coordinates, and that's why I can write this Ex, Ey, and Ez, and so on. So these are really standard Cartesian coordinates for these electric and magnetic fields. I can also combine the current and the charge density to the forecurrent, and once you do it, one set of the equations is simply written as here. It's a divergence of this tensor f mu nu equals to the current. And of course, these are the equations with sources. So they in particular contain divergence of E is 4 pi rho and so on. And then you have the other set of equations, and they are the equations without the sources. So now you can write them in two different ways. So one way is to completely antisymmetrize over all indices. So by the way, this notation comma lambda means d over d lambda. And then you antisymmetrize over all indices. So this is given by 1 over 3 factorial, and then you have all 6 terms, and you go through all the permutations of the indices and plus and minus. Or because f mu nu is antisymmetric, you can actually simplify it, and you just get 3 terms where you take only the cyclic permutations and you add them. And so it's the same thing. All right. So now, of course, if you count the number of these equations, I have, so mu is a dummy index. I'm summing over mu, so that doesn't do anything. So the only free index in this equation is nu. And so you have 4 equations here. 4 equations. And then if I look at this guy here, you are in 4 dimensions. And then you are asking how many completely antisymmetric objects with 3 indices you can write. And it's the combinatoric number 4 over 3 or 4 over 1, which is again 4. Okay, so you have 4 equations here as well, which precisely corresponds to calculating the number of Maxwell equations, right? We have 4 and 4 equations. However, we know that not all of them are sort of independent, that some of them are initial conditions. And the same will be true about these equations. Not all these equations are true time evolution equations. You will have 2 constraints here. Of course, I'm just rewriting it in a new way. So by the way, if you see in differential form notation and you assign to f mu nu a 2 form f, then this equation is simply saying df equals to 0. If you haven't seen these things, don't worry about it. It's saying simply df equals to 0. And then you know by Poincaré's lemma that at least locally there exists a potential such that f equals to dA. So if I set f equal to dA, in other words, if I introduce the 4 potential a mu, then I automatically satisfy these equations here. And this is precisely what we are doing in the 3-dimensional notation, right? We are setting b equals to curl of a, so that we satisfy divergence of b equals to 0, and E is equal to minus gradient phi. And so these are precisely the same things. So if you introduce the potentials, this equation is automatically satisfied. And you can do it in the relativistic notation as well. So in that case, f mu nu is just d mu a nu minus d nu a mu. And once you have the definition here, and you plug it here, you see that it's automatically satisfied, that equation. So introducing potentials kills the first equation. So now let me write one more nice form for this first equation here. And that's in terms of introducing the Levi-Civita symbol. So Levi-Civita tensor So now, of course, we are interested in, so you are familiar with the 3-dimensional one, but the 4-dimensional one is exactly the same thing. So this thing is either +1, -1, or 0. And so you define 1, 2, 3 to be +1, and then even permutations will be +1. And if you swap some indices, you get -1. And if you have two indices the same or more, then you get 0. So in the same way, you introduce this tensor, epsilon, mu, nu, kappa, lambda. And again, this will be +1, -1, or 0. And so it'll be +1 if I have mu nu equal to mu nu rho sigma equals to 0, 1, 2, 3. And then even permutations. And then if you have odd permutations, it'll be -1 and 0. All right, so you have this Levi-Civita tensor, and then you can define so-called Hodge duality. And so let me do it just for this tensor f mu nu. So you say that this is the Hodge dual of f alpha beta, and you define it to be 1 over 2 factorial, and then epsilon mu nu kappa lambda f kappa lambda, or alpha beta. Let's put alpha beta so that we have alpha beta. So what I'm doing here is I'm contracting over these two indices, and so I'm assigning, starting from 2 form f alpha beta, I am assigning a new 2 form f mu nu, star f mu nu. All right? So this doesn't work. So now if you look at this equation here, so you have f mu nu lambda equals to 0, and it's completely antisymmetric. Of course, this object here is also completely antisymmetric. And so if I contract this equation with that object epsilon, that's fine. I'm not killing any symmetric pieces. I'm just preserving all the information. So the statement is, why not to consider that equation over there, but now we multiply with, so I had indexes mu nu lambda, so that's bad, okay, kappa lambda, and then I have f, let's write it this way, d nu f kappa lambda. So this thing is the first Maxwell equation, so it's 0, but I'm contracting with plus minus ones, but all the components are 0, so this must still be 0. All right. And I have this derivative here, but this object is just plus minus 1 or 0, so it's just a constant. So I can actually pull this object through the derivative, right? And if you pull that object through the derivative, then this will be precisely the definition of your Hodge dual of your f mu nu, right? So then you can equally write it as d nu, and then this will be Hodge dual f mu nu, and then you don't have to antisymmetrize anymore. So this is what you are getting. I'm just putting this tensor epsilon through that partial derivative there. And so you see that you can equivalently write this equation. I hope I haven't. Oh, that's fine, probably. So mu nu. Yeah, that's fine. So I can equivalently write the first set of equations as simply the divergence equation. So let's write it in this way so that it's really what we had before. So this is my divergence equation. And now you see a striking similarity between whatever happens with the second equation, where you have the current due to the electric charges, and then you suddenly see that if I take this Hodge dual, by the way, what this Hodge dual does is basically just swaps the meaning of E and B, right? So if I want this starting, so if I want 0, 1 component, then I'll have 2, 3 here, and so 2, 3. So it just wherever I have had E, now the Hodge star will have B, and vice versa. It's just swapping the meaning of E and B in some sense. So now this thing is precisely telling you there are no magnetic currents, there are no magnetic charges. So no magnetic currents. But of course, if they were, it's very simple to generalize this equation to have this, and then you would say this is minus 4 pi j nu magnetic, and so this will be the corresponding magnetic current, and now you have completely symmetric Maxwell equations. Right? So this will be a generalization of Maxwell theory if you have magnetic monopoles, and when these monopoles start moving, you have the corresponding current, and so this will be a generalization of Maxwell's theory. Questions?
You still need to take the Hodge in the side of the derivative because this is a 1 form and this is a 3 form.
This is a 1 form and this is 3 form. Sorry, yeah. Say it again.
If you knew the Hodge, it's still a 2 form. When you take the exterior derivative, you take it to a 3 form.
Yeah.
And the current is a 1 form, so you need to take the Hodge again. In that.
Maybe you're right. Yeah.
Yeah, it's.
No, but this is what I'm doing here. I'm just having some object with one index, so this is fine.
I really think you need to take the Hodge again.
It's contracted there.
It's contracted. You don't need to do.
Okay.
It's in terms of components, not forms.
Okay.
All right. So now we understand Maxwell equations in this notation. The last thing is to understand the Lorentz force law, and for that we need to study the particles, relativistic particles. So you want Lorentz force law. You already know the result, but let's look at it more generally. So you have relativistic particle. And so, if you have your space-time, I'll be writing t here, or what I mean really is ct, and then I'll be writing x here, just choosing one dimension. But anyway, so a point particle or point-like object just sweeps some kind of trajectory through your space-time. Okay, and so you can parameterize this trajectory by x mu of some parameter lambda, and this will be the particle's world line. And so simply this lambda is the parameter where on the trajectory I am. So lambda is the parameter parameterizing my trajectory. Okay. So you can also define the velocity of this particle with respect to this parameter lambda, and it's simply you differentiate these coordinates x mu with respect to lambda. So you would have something like this. It would be the x mu over the lambda, and that would be for velocity with respect to lambda. Okay. So with respect to any parameter, I parameterize my trajectory. So now this is my tangent vector, and now my velocity, I can calculate the magnitude of this velocity. And so the magnitude of this velocity will be simply eta mu nu dx mu over d lambda dx nu over d lambda. It will be the velocity square. So now you get a number at each point of your trajectory. And what is really important is whether that number is positive, 0, or negative. Okay? And the statement is, so if this number is negative, so this is less than 0, you would say that the corresponding trajectory, I don't have enough space here. So we have three possibilities. This is smaller than 0. Then you would say that the trajectory is time-like at that point. If it's bigger than 0, you would say that the trajectory is space-like. And if it's equal to 0, you would say that it's null. So now it is, and this shouldn't depend. So first of all, this is a Lorentz invariant quantity. So I have contracted all my mu nu indices. So this is a scalar. So it doesn't depend on the frame, right? It shouldn't really depend. The sign shouldn't depend on the choice of lambda, as long as lambda is real, right? So if I reparameterize my lambda to 2 lambda, I may change the value on the left-hand side, but I will not change whether this is bigger or smaller than 0. Okay, so this is reparameterization invariant. But of course, this thing in principle can vary from point to point. I can have a crazy trajectory which goes, for some time it goes time-like, then it goes null, then it goes space-like, and some crazy trajectory you can imagine. So now the statement is this is forbidden in nature, and you can actually you have to demand that to preserve the causality, whatever was time-like, in order this to describe the particle, it has to remain time-like all the time. Okay, so to preserve causality, and let me specify to concrete, so massive particles have always time-like trajectories. So you have to invoke an extra principle to actually demand that. Otherwise, everything from this point of view, geometry of parameterizing curves, everything is possible. But you actually describe physics, you are imposing extra condition. So massive particles always time-like trajectories. So in other words, whatever I do with my particle, at every point, I have to stay in the light cone. So hopefully I'm staying here in the light cone. So I have to be always in the light cone. I cannot travel too much in that direction, which I'm always traveling here. So let's do it here. So T and X, so that means always stay in the light cone. What it means is that light cone, that if I draw this thing, I always have to be traveling, inside this thing. I cannot travel too much space-like. Okay. Very good. So now we have this velocity here. Now, if we forget about the lambda, that's something which people like, and they call it invariant metric element. So you can introduce a metric element. So they basically forget about this lambda, and they call something on the left-hand side. So ds square, eta mu nu, dx mu, dx nu. By the way, there are many conventions in special relativity. There will be even more conventions in general relativity. So one of the conventions is the signs of eta mu nu. So I've been choosing time to be -1 and the space to be +1, +1, +1. But also I've actually seen a convention that people put a minus sign here. So when actually Zwiebach was giving here a lecture, and he comes from the high energy physics community, and they tend to put +1, -1, -1, -1 for the metric. So anyway, so when he started lecturing, he put minus plus plus plus, and I was really, really happy. But then he put a minus sign here. All right, so, okay. So I'm defining this with plus. So that's the metric element. And you may be thinking about this, like, this is really showing some infinitesimal distance on my trajectory dx mu. And this is really calculating how big that distance is. And if my trajectory is time-like, I know that this is negative. And so ds squared is negative. So time-like trajectory, so particles, massive particles, have ds squared negative. And so that's why there's this minus sign, which he avoided that way. So now what you can do is that you can introduce a proper time of the particle. And so the proper time d tau. So now I take a minus thing to make it positive, and I take a square root so that this has dimensions of length. Okay, so you just define this to be minus eta mu nu dx mu dx nu. Okay, and so the meaning of this thing is really, if I'm sitting on the particle and moving through the space-time, this is what my clock shows. So this is really the time an observer who is at rest with respect to this particle measures. Okay, time of observer sitting on the particle. And it's guaranteed by this causality or whatever that this thing is always eta mu nu dx nu is always negative. So that's why I'm putting this minus sign here. Becomes positive. I can take a square root, and I have something nice and real. Okay. Questions so far? Yes.
Elaborate on the statement about preserving causality that you have.
I would rather not to. But the reason is that if you would be able to travel to your past if this were not the case. So for example, if you are space-like, you may still think, well, this event happened before that event. However, you can always go to a frame where they sort of swap. And then if you travel, yeah, I think it's really switching from time-like to space-like, which is problematic. Yeah, I would rather not. All right. Less complicated questions. Okay, so now we have this proper time here. And of course, this is a Lorentz scalar. Because it doesn't depend on the frame. All the indices are contracted. And so now I can define physical velocity. So, or, for velocity. The one above with respect to the parameter lambda was like a for velocity with respect to this parameter lambda, or parametric for velocity. So this will be the real for velocity of the massive particle. And I simply define it to be u mu, just my coordinates, over d tau. So now I'm defining not with respect to any lambda, any parameter, but I'm defining with respect to the proper time. Okay. So what is this? So my coordinates x mu are t and x. So this is dt over d tau and dxi over d tau. Okay. But dxi over d tau is dxi over dt and dt over d tau. So now this dxi over dt is what you are used to call a velocity, coordinate velocity, right? So you always take the corresponding coordinate time, and you take this thing. So it's very natural to call this bi, which is the coordinate velocity. So you can write this as dt over d tau 1 and vi, the coordinate velocity. So this is my definition, and this is what it is simply equal to. So by the way, this for velocity is nice and normalized. So if you have u mu u mu, which is what you would call the magnitude of the velocity. Well, what is this? This is eta mu nu dx mu d tau dx nu d tau. But if you look at the definition of d tau, so now I divide everything by d tau, you see that this is equal to -1 from the definition of the proper time. Okay, so this form velocity is normalized to have constant value, and if you want, it's an integral of motion. Right, so no matter how my particle travels, I always have one integral of motion, and that's u squared equals to -1. All right. So what does it mean? So I have that expression for u mu. So I can also calculate it this way. So it's dt over d tau square. And then if I lower the index of u mu, I just pick up a minus sign here. Right? So this will be v square minus 1, vi square minus 1. And this is equal to -1. So you immediately know what dt over d tau is. And you find that dt over d tau is just 1 over 1 minus v square square root of that. This is what you call gamma. The Lorentz factor gamma. Yes?
So maybe a silly question, but for example, photons, d tau is 0. Can you define velocity for photons as well?
Yes, you can. Of course, then it's not the proper time. So for photons, you can still parameterize their trajectory by some parameter lambda, but it's not the proper time because proper time only for massive particles. The statement is many things go through the same way. The only thing is that u mu square now is equal to 0. Satisfies the same equation of motion, the geodesic equation, and so on. So yeah, there are subtleties about the light-like trajectories or light. Yeah, but many things also go through. All right, so we have that. And so you can put as well gamma here. So it's gamma 1 and vi for the components of the velocity. So another thing is that you need a mass of the particle. Mass of particle. And you know, if you have taken some special relativity courses, that it depends on the velocity of the particle. So if I have an observer who sees this particle traveling with some velocity v, then he measures mv, which is gamma times m0, where m0 would be the mass if the particle were not moving. So this is the rest mass. Because it's rest mass, meaning the mass of the particle at rest, this is a Lorentz invariant quantity. I just defined this to be a number, and then this will be true in any frame, right? So this is my mass as the observer sees it if the particle moves at the velocity v, but m0 is the rest mass. All right. So now this is another scalar. And so if you have the scalar, we can use this to multiply some vector to get something new nice, and that's the for momentum. So for momentum, and you define it to be p mu equals to m0, which is a scalar, so that's fine, times u mu. So this is still a vector, Lorentz vector, and this is what it is. Well, let's. What do you mean by for momentum? To to formulate the Newton's law, you also need 4 force, which we will just say as simply a vector which has the meaning of force in the spatial direction, but it's a Lorentz vector. And so then we have the Newton's law to be d mu over d tau equals to the corresponding force. And this is 4 force. Of course, I can take this m0 out, and what it is just du mu over d tau. So I have to divide by proper time, because that's a scalar. Otherwise, I would be, if I just use t, this would be messing up with the vector property of the left-hand side. Right? So this is the 4 force. Questions? So then, once we have this, we can just formulate the Lorentz force law. And as I did yesterday, there is nothing else than you can write down. So you know that the Lorentz force law is just E times E plus V cross B. So this thing is linear in E, linear in E and B, and linear in velocity. So what else it would be? I have a quantity linear in E. I have a quantity linear in E and B, and I have the quantity linear in U. And so that's what it is, apart from a sign. And so this would be dp mu over d tau, and that's your equation of motion for a charged particle, relativistic charged particle in the external field. By the way, so of course, I had to kill one index here, right? So I had f mu nu, u nu, and I'm killing the index nu here. You might think this is not the only possibility. For example, what if I try, as we discussed yesterday in the office, what if I try f nu nu, u mu? Could I try this? It will still be linear in E, it will still be linear in F, it will still be linear in U. Is this possible? Huh?
No.
Because?
It's 0.
Because it's 0, exactly. So this is not a good thing because that's 0. We are tracing over an antisymmetric matrix. We are looking at the diagonal, and of course you see zeros, and so that's why this is 0. So this will not be the right Lorentz force. And then if you think about it, how many things you can write down which are linear in E and F and U, this is the only thing you can write down apart from a sign. Okay? Or some number. Good. So we are done with relativistic particle dynamics. Are there any questions to this? All right, so if not, then I would like to briefly do relativistic field theories. So we had this example of a relativistic field theory, which was the Maxwell theory. But of course, when you are describing more general theories or other theories, and as we started with Lagrangian mechanics, you better start with the action principle. Okay, and so that's the modern approach, that you write down the action and then you look at the consequences and stuff like that. So part D will be relativistic field theories, and that will be, of course, the action principle theories. So now we have the field. We have the field phi, which lives in the space-time, so T and X, or phi x mu. And so you are requiring that this field behaves nicely under Lorentz transformations so that the action behaves nicely under the Lorentz transformations. So the simplest prototype of this action, which now depends on this field. So you have seen that for the string or whatever, that you have to integrate now over. So it's not just Lagrangian dt, but it's Lagrangian density dt, dx, dy, dz, and whatever, right? So it's an integral. If I combine everything here, it's d4x, so this is dt d3x. And then you have the corresponding Lagrangian density, L. And then this depends on phi, but may also depend on the derivatives of phi and may depend on x, mu. Okay, so this is what it is. And now you require that this is nice. In order for this to be relativistic field theory, that you require that this respects the Lorentz invariance, that this is actually a Lorentz scalar. Yes?
Why do you start with the action and the Lagrangian and not with the Hamiltonian?
Or you could start with the Hamiltonian. Although it's actually a little bit more complicated because you have to tell. So here we have done lots of work to unify space and time, right? So now in order to formulate the Hamiltonian, you actually you have to split the space-time into time again and space. And then do the Legendre transformation in the time direction and stuff like that. So this is the covariant approach, where you sort of treat space-time nicely together and everything is manifestly Lorentz invariant. In the Hamiltonian approach, it will not be. So of course you can do it. You can do it, and you will do it. And for quantization, it's simpler to quantize the Hamiltonian thing than the Lagrangian one, typically. So we will start in your QFT1 course by actually writing the Hamiltonian and stuff like that. But the truth is that the approaches in the end are just a matter of taste, I would say. All right, so we have this. And now we impose the action principle. So we require that delta S is equal to 0 to find the equations of motion. Again, this is our normal delta. It's not delta tilde. So it's just touching the phi's, but not touching the x's. Okay, so this is an integral over some domain omega d4 of x delta L. And whatever I have done for the particle remains exactly true here. So I'll have dl over d phi delta phi, and then I'll have dl over d mu phi delta d mu phi. And that's it. d4 of x. I already have that. So now we have delta and d mu phi, which of course is d mu delta phi. So all you have to do is just move this derivative onto that term. And you can still do it. So now you are picking, so this is your boundary omega, space-time boundary omega, and that space-time domain omega, and that has some boundary partial omega. So of course, when you are integrating by parts, you will pick up a boundary term which lives on this d omega. Okay, and so integration by parts, and you get an integral over omega, and then dl over d phi from the first term, and then integration by parts brings me a minus sign and brings the d mu derivative on this thing, d mu dl over d mu phi. d4 of x. But I have also a boundary term, and that I will write in a stupid way, d omega. So now what it is really d3x, and then the boundary has some normal, and mu, I don't know which direction it should go, doesn't matter for us, and mu, and then dl over d mu phi. Okay, so that's the boundary term. Of course, you have to tune which direction and mu goes in order this to be true. So really, I am using Stokes theorem, turning the volume integral into the surface one, but it's like doing the integration by parts. Right? So when we had the total derivative of time, which brought us the boundary term, and it's just this thing. Delta phi. Okay, so now this is whatever is happening inside the boundary, so it better be 0, and that's my Euler-Lagrange equation. So the Euler-Lagrange equation now is just dl over d phi minus d mu dl over d mu phi equals to 0. That's my Euler-Lagrange equation. And then better my boundary term be 0. But you see that I can make the 0 provided that I choose delta phi on the boundary to 0. It's precisely what we are doing, fixing the endpoints. Now our endpoints are actually boundary, but so I'm fixing my phi variations on the boundary. So I'm fixing phi on the boundary and asking what's happening inside. So if delta phi on the boundary equals to 0, then this term vanishes, and I have 0 variation of the action. Yes?
What do you mean by this d mu? So
this is what I define as d over dx mu.
Yeah, but if L does not depend explicitly on space-time coordinates, then this would be
so phi depends on x mu.
Yeah. So
right. So even if this is not the case, so this still depends implicitly on the coordinates.
Yeah, so d mu is actually total.
So what is this? Is that I look at the L, and do I see any derivatives of phi in L? And you will see immediately an example. It's just free scalar field. It contains d mu phi, d mu phi.
Yeah.
Right. So I just differentiate with respect to the symbol. Right. And then the result depends on x mu implicitly.
Yeah.
So I just differentiate with respect to x mu.
So this would actually be Roman d, not a partial.
Roman d. I don't know, it depends on time as well, right? So this is nothing else than whatever I was writing before, dq dl over dq minus d over dt, dl over dq dot goes to 0. So now, so this is like one-dimensional case. I had only time.
Yeah, but
now I have time and space.
But that's total, and the other one is partial.
Right, but this is total because I have only one. I have only one. Yeah. But you just think about it like I have more times, which some of them are space, but anyway, so I just, instead of q dot, I have to write down all the possible derivatives with respect to all possible coordinates. That's why this is partial, because now I have more than one. I have t and x, right? So, yes?
So, in classical, when we started with classical physics, the action, the Lagrangian approach and the Hamiltonian are supposed to describe the same physics. But in this, in relativistic field theory, or even more general, in order to define a Hamiltonian, you need to be able to split in space and time. And in order to define the Lagrangian, you don't need to do that, right?
That's right. Yeah.
So,
well, there's a way how to do it. You can always split space-time into space and time. There are ways how to do it.
Not always.
Yeah, there are some topological restrictions if you want. So really, your space-time has to look like R times R3. So then I can split into time and space. So that's the only restriction. So we have like some topological restrictions. But otherwise, I can always split it.
But if you have a background spacetime that cannot be decomposed like that, but you can still write the Lagrangian.
Possibly, yeah. So these things are, of course, equivalent for most of the cases. It's maybe possible that there are some cases where if you start one description with one description, you cannot get the other, or it's actually painful to get the other. So typically what happens when you actually go to the Hamiltonian is that you pick up some constraints, as we have seen, so for the gauge theories, and so now suddenly you have constraints in your Hamiltonian description, and it's quite ugly. So that's why I'm starting with the Lagrangian description.
Is that boundary there, is it a time-like boundary, or I can choose it as whatever I want?
You can choose whatever you want.
All right,
So this boundary will be somewhere time-like, somewhere space-like, whatever. So I have piece of space-time, right? So I will have some time-like boundary, some space-like boundary.
So that dx to
Okay, very good. I knew why I wrote it that way, but I just wanted to make it. Thank you.
okay.
So here I don't mean really the spatial direction. Let's write it the way I write it in the text. D3 sigma nu mu. And so this is whatever the metric element on the boundary is. And it has some normal. Thank you. Other questions? All right, so we have the Euler-Lagrange equations for the field. So now we can play the same game for the Noether's symmetries. So we knew that in classical mechanics, if you had some symmetry of the system, then we had the corresponding conserved quantity. And how we found that we have a symmetry in the system is that we did some variations of time and of the coordinates, and we observed that this leaves the action invariant, right? So now our action is function of phi, but also of the space-time coordinates x mu. So now I can do transformations on my space-time coordinates x mu, and I can do transformations on my fields. And if I see that the action actually remains invariant, then I have a symmetry. Okay. So Noether's theorem. It will be the field version, which is probably version number 5. So again, let I have delta x mu and delta tilde phi to be a nice continuous symmetry. So global continuous symmetry of the action. That is of shell so without imposing the Euler-Lagrange equations, I find that delta tilde s equals to 0. That's what I mean, global continuous symmetry. So let's you find such a transformation. Then the statement is that you can find a current which is conserved, and then if you have a current, you have also conserved charge, right? So let me state what this current is. So then you can find J mu, which is given by T mu nu canonical delta tilde x nu. I will tell you what T mu nu canonical is, but it's energy momentum tensor if you heard that about it. And then plus dl over d T mu phi delta tilde phi. Okay? And so you have this current, and this is conserved on shell, meaning d mu j mu equals to 0. But we know that whenever we have continuity equation like that, we have the corresponding conserved charge. So this is what we've seen in the Maxwell theory, right? So we have rho and j. So this is an analog of d rho over dt plus divergence of j equals to 0. And so we know that if you define charge to be an integral over rho, then this will be conserved in time, provided there is no flux through the boundary. So you will have the conserved charge. So now what is T mu nu canonical is the energy momentum tensor, but the canonical one. Canonical energy momentum tensor. And you have the following description for it, or prescription. It's simply given by T mu nu canonical to be eta mu nu L. Of course, so this is my eta, the metric, but now I rise one index, so this is really delta mu nu. Doesn't matter. And then minus dl over d d mu phi, and then d nu phi. Okay, so this is a beautiful formula for the canonical tensor, canonical energy momentum tensor, and this is even more beautiful formula for your conserved current. So this is a field analog of your explicit version of Noether's theorem for the particle, and you will see that if you actually trying to go from space-time to just time, so and from fields to coordinates, it will reduce to whatever you have seen for the particle motion. Okay? So are there questions to this? Yes?
Just wondering what's the difference between delta tilde and delta?
Oh, it's still the same thing. So I define delta of phi such that it's phi prime of x minus phi of x. So I'm keeping x the same, but I'm just changing the field. Whereas delta tilde, I can change x as well, right? So again, in the same way as I could change the t in the particle case, is when I had the tilde things. So delta tilde phi is just phi prime x prime minus phi of x. And if I have instead of prime here just x, that would be just delta without the tilde. So it's exactly, proceeds the same way. The proof also proceeds exactly the same way. So you have gone through this proof in your tutorial, and in the lecture, the first lecture, we have done that. So now the proof goes exactly the same way. So there's basically no difference except you have now space-time, right? So I've put it in the text, and you can read it through. It's exactly the same long as the previous proof, and it's rather simple, but it would just take me, 10 minutes, which I don't want to spend on this. So you can prove this very easily. So now let me consider an example of this theorem. So this we don't need, and this we don't need. So this is our beautiful theorem. And so you may have an example, and you may consider space-time transformations. So you know that your fields are typically nicely behaving. In order this to be relativistic, they are behaving nicely with respect to the Lorentz transformations. But most of the field theories are also behaving nicely with respect to the Poincare transformation. So if you translate in space and time, it doesn't matter, right? So I can do Lorentz transformations, but I can do also translations. So let's consider this case. So invariance with respect to space-time translations. Space-time translations. And so what I mean by this is that my delta tilde of x mu is I can now shift in space, and now I can shift in time. But this has to be a global continuous transformation. So I have to be able to do it infinitesimally. So that's why there will be an epsilon. And it must be a global one, so this epsilon does not depend on space, time coordinates. It's just a constant. So delta x mu, I can choose epsilon mu. So I can move, epsilon 1 this direction, epsilon 2 in that direction, epsilon t in that direction, and so on. And I'm not doing anything with the fields. Okay, so I'm just doing this. Yeah, so when you are deriving the energy, remember, you just consider the time translation, and you were not doing anything with the coordinates. So this is precisely this. So what you expect is that what should be conserved is energy, but now I also move in space, so I should also conserve momentum. So this should have as a consequence that I conserve not only energy, but also the momentum. And of course, this is the case. So what is the corresponding current? If you look at this formula here, the corresponding, so delta phi is 0, delta x nu is just epsilon nu, right? This constant, I can forget about it. And your current is actually this T mu nu. And for each epsilon, I have this T mu nu, right? So I have actually 4 conserved currents. So let's name them J mu and then nu. So this is, that I have 4 currents. 4 currents. This index nu is the same index as whatever, but it's simply given by T canonical nu, right? So if I choose nu equal to 0, I will have 1 conserved current, T mu 0. Then I'll have, if I choose nu equal to 1, I will have another conserved current, G mu 1, which is T mu 1, and so on. So now nu equal to 0, of course, should give me, okay, so that's 1 conserved current, but the corresponding conserved charge will be the energy. And nu equal to I will give me that the momentum is conserved. Okay, and I have 4 conserved currents. That's why I have 4 conserved quantities, energy and momentum. Of course, what I'm saying here is that on shell, this will be only true on shell. These currents will be conserved on shell. That means that J mu partial mu is equal to 0, but that prescribes into T mu nu canonical equal to 0 for any nu. And sometimes people call this conservation of energy momentum. That's a conservation. So who hasn't seen this? Okay, some people hasn't. So I hope this is just a direct generalization of what we are doing with the particle. But it has more indices, it looks more formidable and so on, but it's basically the same thing as what we were doing with the particle. Okay. Are there any questions to this? If not, then let me just prepare the tutorial today. So you will be playing with a relativistic field theory. Surprisingly, the Maxwell's theory. All right. So now you will derive the Maxwell's theory. In other words, what you'll do is that you will derive the Maxwell's equations 1, 2, and the Lorentz force law from the corresponding action. Right? So what I will ask you to do is to actually vary this action, which I'll just write down for the Maxwell's theory, and derive all the equations of motion there are to be derived. So in other words, Maxwell's theory can be formulated from the action principle. All the action principle is a little bit sneaky, and I will explain why. So if you look at these equations here, they all contain only F mu nu. Right? So I'm writing all these equations in terms of F mu nu. So you might think I can write down the action where my field is F mu nu, and that will be, and then by varying this action with respect to F mu nu, I get my equations of motion. Nobody was able to do that. Okay, so the reason why this is not quite obvious to me, or why you cannot really do it. But maybe it's just telling you that F mu nu is not the right field for the Maxwell theory. What you have to do is that you have to write the action in terms of the potentials. So you are not writing in terms of F mu nu, but you are writing in terms of these A nus, in terms of the potentials. Once you do that, you actually can derive these equations. So the action is a function of the potential. All right, and so I hope this is fine. So action for Maxwell, and I see there won't be any scalar field today. So your action will be a function of the vector potential, of the potential, and I'll be considering, so in order to derive this Lorentz force law, let's just derive it for an electron. So I have a point particle, massive point particle carrying charge E. And let's be asking, so this is a test particle in the theory. So I'll be putting into my action not only the field, the electromagnetic field, but also the corresponding Lagrangian for the charge point particle. Okay, so this charge point particle lets its trajectory be described by a quantity epsilon nu. So this is the potential, and this is the electron's trajectory. Okay, so now what is this? I'll write down the result. So it's 1 over 16 pi, why not? Okay. Then you want to write down this Lagrangian density. So you want to really write, is it still somewhere here? You want to write d4x, and then the corresponding Lagrangian density for the Maxwell field. Okay. Well, what it could be, if you studied electromagnetism, you know that the energy is something like E squared minus B squared. Okay, so that's the energy density of things. So now, if you use this prescription for F mu nu, what you find that E squared minus B squared, which is the energy density, is precisely F mu nu, F mu nu. Try it. Okay. So then it's obvious that I want to write something like energy density. So I'm writing F. What is it I'm writing? F mu nu, F mu nu. And that's it. That's indeed all you need to do for Maxwell field itself. Okay, so just writing the energy density. Right? So now, so this is just the Maxwell field on its own. But be careful. So here I'm writing it in terms of the field strength F mu nu, but this is a function of A mu. So really what I mean here is that F mu nu is T mu A nu minus D nu A mu, right? So I have to plug it there and plug it here, and then I have it in terms of A mu, right? So that's the first term. So second term is that you want to add this massive charge particle. So by adding the mass particle, the massive particle, you put a minus. This is my rest mass of the particle. And then we will see in a minute is that what you have to basically, so you want to extremize something. And so how does a free particle move? So free particle move on the straightest line, or the time which actually takes the least time. Okay. So now if you're in special relativity, because of this screwed up minus sign, actually you want to maximize the proper time for the particle. So what has to be here is basically d tau. So this is minus m0 d tau, and that will be the action for a massive particle. But I can write down d tau in terms of the formula which I wrote before. It's eta mu nu, dx mu, dx nu. And I can parameterize the trajectory of this particle with any parameter lambda. Okay, so I just write d lambda here, which is any parameter here, and then it's just minus eta mu nu, dx mu over d lambda, dx nu over d lambda. Okay, but all what it is just minus m0 d tau, and it has very intuitive thing is that I want to maximize the proper time of the particle to get the straightest line, which is how the particles actually move. Okay, so maximize. Proper time, and then I did mistake, of course. So I'm parameterizing the trajectory by y. So y mu, y nu. Sorry for that. Okay, so that's the second term. So now I have free relativistic particle of mass m0, and then I have free field. right? Well, in principle, they can live next to each other, but if the particle has charge, there will be an interaction between the two, right? So the particle will be interacting with the field. And the statement is that the interacting term is precisely proportional to the charge of that particle. And, well, the interaction in the Maxwell equations is, so this is my current produced by the particle. So it's through this current, right? So the interaction will be, the current is interacting with my field, with my Maxwell field. But field is described by the vector potential. Okay, so there's only one scalar quantity I can write down, is J nu A nu. So this will be something like E A nu J nu, where this is my current, this is my field. But I have to write it in a way, so of course this A nu has to be non-trivial only on where the particle is, right? So my current J nu is just, I'm moving a charge with some velocity. So to get the current, you take the charge times the forward velocity of the particle and you get the current. Okay, so now I write it in this way. There's d y mu, a mu, at, in lambda. dy mu over dA mu. So now if I divide by lambda here, then this is my forward velocity. So my forward velocity times the charge is the current. So I have the current times the field, and that's what it is, d lambda. Okay, so this is the interaction term.
Sorry.
Yes?
Probably a dumb comment, but shouldn't there be a minus sign because it's an electron and...
Whatever. So I was playing.
I agree, whatever.
I was playing with the signs, and I want really to get the signs which are written here. So I want plus e here, and I want minus 4 pi here. So I really want to recover all these equations here, and so I tune the signs so that this is the case, right? But yeah, the electron may have negative charge and stuff like that. But so I'm just really tuning the signs so that you get the right equations of motion. Okay, and this is the Maxwell theory of electrons, right? The beautiful theory is described by just this by this very simple action, and you see this is really simple. It's just maximizing proper time. This is just the energy density of the electromagnetic field, E square minus B square. And this is just the simplest interaction current times the corresponding Maxwell field. And that's it, right? And so it will be now up to you in your tutorial to actually show that if I vary this action, so variation with respect to y mu should give me the Lorentz force law. And the variation with respect to the field should give me the Maxwell equations. And you will show that in your tutorial. Yes?
Is the negative 1 over 16 pi multiplying everything in that?
No. So here I have minus 1 over 16 pi, just the first term. And again, it's so you know that may not be standard, but it's because I'm using these strange units where I don't have any epsilon 0, mu 0, but I have just the velocity of light equal to 1, and I'm putting these 4 pi's here. So it's minus 1 over 16 pi just in front of the first term. I hope that's correct. I was really playing with these numbers and pluses and minuses so that you get those equations. I hope you do.
Maybe it's still a trivial question. Why do you want to maximize the proper time? You don't want to minimize it.
Okay, it has to do with this minus sign in the eta mu thing. So you're putting this minus sign for the time direction. It's just one of the miracles of special relativity.
So basically, they are minimizing the absolute value in essence.
Yeah, so what you are... Yeah, so if you have ds square is eta mu nu dx mu dx nu, you would be minimizing that ds, but that means the other way for d tau. Yeah, it's just one of the miracles of special relativity. Other questions?
We're not going to get this first set of equations, though, from this, right?
Are we not? So, of course not, right? Because they are already input to our action, right? So we are saying we cannot write the action in terms of f mu nu and derive all sets of Maxwell equations. That's how I started. I told you we cannot do that. Nobody knows how to do it. So instead, we treat the action as a function of the potential. But once we have that the field strength is given in terms of the potential, then this equation is automatically satisfied. So we're basically cheating, and we are not deriving this equation because we are saying f mu nu is not the right field. You can write down the action, but you have to write it in terms of a mu. All right. So I just want to write the last formula about this. So now you see this currents and whatever. This action is of course invariant under the space-time translations. And so then you have the corresponding current, which is just the canonical energy momentum tensor, this one here. Okay, so now the formula is given here, so that's your canonical stress energy tensor. You will also calculate it in your tutorial today, and you will find something strange at first, is that the canonical stress energy tensor, which you find here by this prescription, is not nice. It's not nice for two reasons. What people typically want from the energy momentum tensor, that it is symmetric. If I write this index here, that the energy momentum tensor is symmetric under the exchange of indices. So it's the symmetry which people like. And another property is that, well, this is an energy momentum tensor of the electromagnetic field. So it should be gauge invariant. It shouldn't depend on what kind of A I choose. It should be expressible only in terms of f mu nu, right? So now when you calculate this thing here, you find that it's not true. First of all, it will not be symmetric, and second of all, it will not be gauge invariant. So canonical tensor as given by this prescription here is not symmetric, and not gauge invariant. Okay. So, however, you can add some very nice term to this thing here, so that the resulting object is still conserved. And so, upgraded tensor is already symmetric and gauge invariant. And you have this beautiful formula which you've probably seen many times. So this is not canonical one, it's just the upgraded mu nu, and it's given by 1/4 pi, and then f mu alpha minus 1/4 eta mu nu f alpha beta. And so you've probably seen this energy momentum tensor for the electromagnetic field, but I'm just really trying to stress here that this is not what you get by straightforwardly applying this Noether's procedure. You have to upgrade it by making it symmetric and making it gauge invariant. So this only depends on f mu nu, doesn't depend on A explicitly.
Does this come from adding some total derivative to the?
It comes from adding a term which whose divergence is 0. Yes, exactly. And you will see what the term. So basically, from the prescription, you sort of see what the term has to be. And of course, there are ways how to actually do it systematically, how to find this term. Although in this case, it's much simpler to actually just guess that you should be adding this term. But yeah, you have to upgrade the tensor. All right, so now Dan will kill me because I didn't have time to discuss the scalar fields. And so, but if you are interested in, so scalar field theory just provides another example of relativistic field theory. Just take a different action, and you can derive Euler-Lagrange equations. You can derive the corresponding energy momentum tensor. And so with the real scalar field, which of course gives you the equation d square minus m square acting on the scalar field equals to 0. Some people have seen already, it's the Klein-Gordon equation. You'll be playing half of the time in the QFT1 course, right? It's just a trivial example of what you are doing here. So now what is less trivial is to make the scalar field complex. So now you have phi, but you have also a similar equation for phi star. So if you make the scalar field complex, suddenly you have 2 degrees of freedom, like a real part, an imaginary part, or phi and phi star. Okay? This allows you to actually have a conserved current, and complex scalar field can carry the charge. Okay? So the real scalar field cannot. The complex scalar field can carry charge. So now if you look at this theory which we are building here for electromagnetism, so we have went only halfway, right? So we have described the electromagnetic field, well, with the field, right? We have FP nu, that's the field, but we still describe the matter by simply a point particle, right? So the matter is just particle dynamics, whereas the field is actually field theory. So now the simplest way how to make an amendment, so how not to go halfway, but how to go full way to the field theory, is to replace the matter with the complex scalar field. Such a complex scalar field can carry the charge, and what you are getting is a scalar field quantum electrodynamics. Okay, and so you will do that in the second part of the QFT1 course. But of course, this is still not good because the scalar field does not carry the spin. And you know that the electron actually has spin. It's a fermion, it has spin 1/2. And so this is not good to describe the electron by the complex scalar field, but rather you have to describe by the Dirac field. Okay, and so then if you replace the matter with the Dirac field, plus you have the Maxwell field, you have the quantum electrodynamics as you will see it in the second half of your QFT1 course. Okay, that's something to look forward to. So let me stop here. I hope you had some fun. And so there's many ways to go from here. As I said, you can go and quantize things. You can replace the matter, replace it with fields, quantize the thing. We are going in the QFT direction. Of course, here we have interaction with the electromagnetic field. From classical point of view, we have also gravitational field, right? And so that will be the part of the relativity course, and we will try to extend this into the presence of gravitational field. Okay, so let me stop here.